In this video, we're going to look at how to measure standard electrode potentials, what those values actually mean, and how they can be used to predict reactions at each electrode. So to start off with, we first need to have a bit of an understanding as to what an electrode potential is, and there are kind of two ways of us thinking about this, both of them very much interlinked. The first is that we could think of an electrode potential as being the measure of how easily a substance is oxidized. In other words, how easy it is for that substance to lose electrons. Our second way of thinking about it is as a measure of the ability of a half cell to push electrons away. For us to understand these, we need to look at a half cell in a little bit more detail. So here we have a half cell with its reversible reaction. Now, the electrode potential of any half cell directly relates to the position of the equilibrium within that reversible reaction. Now, the more easily a substance is oxidized, the further towards the side of the oxidation reaction, towards the side with the ions and electrons, the equilibrium lies. As a consequence of this, we get a bit of a buildup of electrons. Now, our electrons being negatively charged, and like charges repelling one another, this buildup of electrons starts to create a bit of a repulsion. It wants to start pushing electrons away from the half cell. And where this is the case, we get a more negative electrode potential. If, however, we had a substance that was less easily oxidized, the position of that equilibrium is going to lie further to the side of the reduction reaction, towards the side with the atoms. We're therefore going to get less buildup of electrons, which is going to result in a lower repulsion, so that half cell isn't going to be pushing electrons away from it as strongly, and this would provide us with a less negative or more positive electrode potential. So the more negative an electrode potential is, the more easily that substance is oxidized, and the greater the ability of that half cell to push electrons away. And the more positive an electrode potential is, the less easily a substance is oxidized, and so the weaker the ability of that half cell to push electrons away. So now that we know what electrode potentials are, surely it's just a case of us connecting them up to a device that measures the electrode potential. Well, this becomes a bit of a stumbling block. Electrode potentials cannot be measured directly. Voltmeters will measure the difference between two electrode potentials, something we refer to as the potential difference, but they cannot directly measure the actual electrode potential of any half cell. This is where the standard hydrogen electrode comes into play. It acts as a reference point for us to compare all electrode potentials to. A standard hydrogen electrode has hydrogen gas being bubbled into a solution that contains 1 mole per decimeter cubed of aqueous H+ ions. Now that solution is often a 1 mole per decimeter cubed solution of something like hydrochloric acid or maybe even nitric acid. One thing you do need to be careful with is that if you are using sulfuric acid, which is a diprotic acid, you would only need a 0.5 mole per decimeter cubed solution of sulfuric acid to produce a 1 mole per decimeter cubed solution of aqueous H+ ions. The other thing to bear in mind is that some exam questions require you to name the solution. So just saying a 1 mole per decimeter cubed solution of H+ ions isn't going to be enough. I would personally recommend just sticking with either hydrochloric acid or nitric acid, because then you just need a 1 mole per decimeter cubed solution of either of those acids to give you the 1 mole per decimeter cubed solution of aqueous H+ ions. Now that hydrogen gas needs to be bubbled in with a pressure of 100 kilopascals, and the whole system needs to be kept at 298 Kelvin. There is also a platinum electrode that is used as a surface for the oxidation or reduction reactions to occur on. Now, as with metals in solutions of their ions, this is going to establish an equilibrium between the hydrogen gas being oxidized and the H+ ions being reduced. We use the standard hydrogen electrode as a standard reference point, and by definition, its electrode potential is 0.00 volts as long as it is under standard conditions. But the key question at this moment in time is, why are we using a platinum electrode? In any half cell, the oxidation or reduction reactions occur at the surface of the electrode. Therefore, electrodes must be made from a solid that can conduct electricity so that it provides a reaction surface that allows the transfer of electrons. Typically, half cells use a solid metal in a solution containing the ions of that metal. But hydrogen is a gas at room temperature, so there's no surface for the reaction to occur on, and it doesn't conduct electricity, so won't allow the transfer of electrons. So scientists needed to find an alternative. Platinum is used as our alternative for two reasons. Firstly, it's a solid that is inert or unreactive, so it won't react with the solution of H+ ions inside of our standard hydrogen electrode. Secondly, it conducts electricity, so it will allow the transfer of electrons necessary for the oxidation and reduction reactions to occur. Now, platinum electrodes aren't only used in a standard hydrogen electrode. They're also used for half cells involving other gases, or if you have half cells involving solutions of two aqueous ions of the same element, such as Fe2+ and Fe3+ ions. In this example, we can't just use an ion electrode, as we'd be setting up three different reversible reactions. One between the ion electrode and the 2+ ions, another between the ion electrode and the 3+ ions, and finally the one between the 2+ and 3+ ions themselves. Since platinum is inert, we can use it as our electrode in these cases to ensure that only the reversible reaction involving the two ions of the same element can occur. So how do we use our standard hydrogen electrode to measure the electrode potential of other half cells? Well, first we need to connect it to another half cell. However, by convention, the standard hydrogen electrode should always be placed on the left. This just helps ensure that all standard electrode potentials are being measured in the same way each and every time. The two half cells also need to be connected externally by a voltmeter. The voltmeter has a very high resistance, so almost no current flows, but crucially it will measure the difference in potential between our two electrodes. Since the electrode potential of a standard hydrogen electrode is defined as being 0 volts, the potential difference reading from the voltmeter must be the electrode potential of the other half cell. The difference between any number and 0 is always going to be that number. Now, it's important to note both the magnitude, i.e. the size of the reading, but also whether it is a positive or negative value, as this will be really important when interpreting standard electrode potentials later. Finally, we must make sure our electrochemical cell is operating under standard conditions. But just what are standard conditions and why do we need to use them? Well, since the electrode potential of a half cell is dependent upon the position of the equilibrium within that half cell, conditions such as temperature, concentration, and pressure if gases are involved are going to affect the electrode potential of a half cell. If we use our standard hydrogen electrode as an example and increase the concentration of H+ ions, well then due to Chatelier's principle, the system is going to oppose that change and it's going to favour the reduction reaction, shifting the position of the equilibrium towards the left in this case. This would mean that the electrode potential of the hydrogen half cell would no longer be the same as what it was at that lower concentration. For our hydrogen electrode, this would mean that we could no longer say its electrode potential was 0, as that is only the case when it's operating under standard conditions. So just what are the standard conditions that we need to remember? Well, firstly, any solutions in either half cell must have a concentration of 1 mole per decimeter cubed. Secondly, the temperature of the two half cells must be 298 Kelvin. And finally, if we're using any gases, they must have a pressure of 100 kilopascals. It's really important that you learn these conditions. Examiner reports suggest that many students can't actually identify them accurately. Also, exam questions might sometimes ask you why an electrode potential obtained doesn't match the standard electrode potentials given. If this is the case, standard conditions weren't being used, so you need to go back and read the question carefully to identify which condition wasn't being met. Okay, so great. We've got these standardized values, but why are they actually important? What use do they have? Well, standard electrode potential values can be both positive and negative, and both the magnitude, the size of it, and the sign, positive or negative, are important, as this will ultimately allow us to deduce which substance will be oxidized and which will be reduced, as well as identifying which half cell becomes the positive or negative electrode within our electrochemical cell. So let's take a look at what these values mean. If the value of a standard electrode potential is a negative value for any particular substance, it means that that half cell is more easily oxidized than what hydrogen is. And if the standard electrode potential for a substance is a positive value, it means that the substance is less easily oxidized than hydrogen. And when thinking about an electrochemical cell made up from its two half cells, the half cell with the more negative electrode potential is more likely to lose electrons. This means it's going to be oxidized and would therefore become the negative terminal. The substance with the less negative, or more positive electrode potential is more likely to gain electrons. It will therefore be reduced and become the positive terminal of our cell. If we then replace the voltmeter with a component that allows a current to flow, electrons would move from the negative electrode through the external circuit to the positive electrode, generating an electric current. So in this video, we've seen how standard electrode potentials are measured and what they tell us about redox behavior within an electrochemical cell. For your exam, you'll need to be able to interpret standard electrode potentials and describe how the standard hydrogen electrode is used to measure them, as well as the importance of standard conditions. Stay tuned for the next video, as we're going to be looking at what the EMF of a cell is and how to use standard electrode potentials to calculate it.